Hi everyone, welcome to this section 2.3 video. In this section, it's actually going to be fairly quick. We're going to be looking through some examples of how to do limits without having to go to the graph table and kind of visually look at things. So the first thing we're going to be looking at, which is going to be really useful, is called the direct substitution property. That's this first box here. And that says if we're taking the limit of some function f as x approaches a, where again, a is just some point that some x value we're trying to get closer and closer and closer to. Well, if it happens that f is a polynomial or rational function and a is in the domain of f, which means I can plug it in, get a number, then it's super nice. This limit here is just the function value. So because it's a polynomial or a rational function with a in the domain, I can just assume the limit will exist, and the way to get there is to just plug in a. It's super, super nice. So you're going to hear me say later in the video all the time, plug it in. Okay? And so what we're going to do is we're going to look at a bunch of different problems where our goal is to try to get into this, okay, this direct substitution property. Can we get to the point where all we have left in our limit is a polynomial or rational where a is in the domain? Now, a lot of the problems you're going to see me do, I just try plugging it in to start just to see what happens. And that's a fine place to be because this method will work for other functions as well. It's not just polynomials and rationals. It can work for other things. So you'll see me just use the plug it in and see what happens. What will happen in some of these is that we're going to do this plug it in method, and then we'll realize, oh, it's not quite working. I have to do something to my function f here in order to try to get it into the right form, in order to do some cancellation, just algebraically manipulate it so that I can actually use this direct substitution property. And that's what this next box below actually says that I can do. If two functions are equal for some inputs, x, then their limits should be equal, given that there is a limit. And so all this is saying that, this seems kind of maybe like abstract, or maybe it's kind of like, well, yeah, so what? All this is saying is, let's say you have this to start. Well, you're pretty sure the limit exists. You want to try to plug in, like we're doing above, and things just aren't quite working out. What that means is that if you can start with f of x, do some algebra steps, which we'll see some examples of, and maybe it's multiple steps, and get to a function g of x that looks different, but algebraically they're the same. You just, move some things around. You'll see what kind of stuff we're going to do in a little bit. But they're still the same function on these x's near a. Then being able to take the limit here, like let's say you can do that one, well, great. You actually now know the limit of your original problem. So that's the idea. That's what this tells us is an actually okay thing to do. You get a function, maybe it's too complicated, something's weird happening when you plug in a, do some algebra, get to something simpler. Might always not look simpler right away, but in terms of plugging in a, it'll be simpler. Get the limit, and you've solved the problem. All right, so that's just what this piece says to us. And then the second theorem here is actually something we've already been relying on, which is the limit exists if and only if the two-sided limits both exist and are equal. So we've been thinking about that already. We did that a lot in the last video with the graph and the table, making sure that we looked from the left, we looked from the right, and those gave us the same number. So that's just restating something we've already kind of thought about. All right, so that's it. That's all 2.3. So how does it work? Well, we have this limit here. And what I've done for each of these is I've immediately plotted them. And this is not something you have to do, but I think it's a good first step when looking at a problem is just graph it. Now, I've done these in Mathematica. If you have a calculator, it'll probably be a lot quicker to graph it in the calculator, and that's fine. But getting that picture up and making sure that we're plugging in values that, actually give us the picture we want. So the limit as u approaches -2. So I've made sure -2 is in this picture. So make sure you're always doing that too, thinking about that when you're graphing it. But what I'm seeing here is, and pictures can lie a little bit, but just kind of looking at this quickly, it does seem, as I go from the left, I go from the right, it seems like there is this specific y value, maybe it's 4, who knows, we'll figure it out. It does seem like the function is approaching from the left and from the right to one specific number. Okay? There don't seem to be any asymptotes. It seems like the function's defined all over this little area between, really it looks defined between -4 and 4. That's something else we could think through. But specifically, it seems like we're all good here, we're defined, and we're approaching the same number left and right. So that's making me think like, okay, yeah, there's a limit here. And it just so happens actually that I think the function's defined at -2. So to recap kind of the way I'm looking at this, number one, the limit looks like it exists. So I know that's a weird thing to say, right? It looks like. But sometimes that's what you have to deal with when you're just looking at a picture. Well, it kind of looks like it should exist. Okay. And number two, it looks like the function is defined there, which we don't need. Remember, we don't need that for the limit to exist or to find it. But if the function is defined there, that can help us figure out the limit. And that's just us going off of this idea here, which specifically was for polynomials and rationals, right? Which we don't actually have here. But often we can still use the idea even if we don't have a polynomial or rational. So I'm looking at this picture, I'm seeing, yep, left and right looks like it's going to the same point, number one. Number two, it looks like it's defined there. So with both of those things in mind, I'm just going to try plugging it in. So we go over here, and the first thing we try is plug it in. What do I mean by that? I mean take your a, which is -2, and plug it in to the function. So that would be -2 to the 4th plus 3 times -2 plus 6. Okay? And so at this point then it's just, can we figure out what this equals, right? And so you can, if you got a calculator, you can do it in your calculator, you can do it by hand, doesn't really matter. I'll just do it quickly because I forgot to get my calculator out. 16 minus 6 plus 6, which is root 16, which is 4. So what just happened? We took the limit by plugging it in. Why did we feel comfortable to do that? Well, it looks like the limit exists. Left and right's coming to the same point. Left, it's coming down, kind of looks like 4. From the right, it's coming up, looks like 4. And then it also looks like the function's defined at that point. There don't seem like there are any holes or jumps or asymptotes or anything crazy like that. It looks like it's defined, so we give it a shot. Plug it in. And if you go through and you look at this picture, it seems to match 4. If you look at a table of values and get closer and closer and closer to -2, we're going to get closer and closer to 4. And so what we found is that the limit as u approaches -2 of this function, u to the 4th plus 3u plus 6, that's equal to 4. Boom. And that's it. Plug it in. The plug it in method. That's often going to be our first start. It's not always going to be the way we do it. It's not always going to work right away. You might have to mess around with some stuff. But it's a great first step, especially when you have this picture in mind and you're kind of thinking like, yeah, okay, I think this is going to work. So let's try a new one and see if this holds up. So I've got a rational function. Okay, so let's think about this. I've got a rational. So that immediately makes me think back up here. Oh, rational function. Now, in order to use this direct substitution property, we need to be thinking about this value, a, that we're approaching. Is it in the domain? Now, here's the tough thing. Just looking at this can be tough to figure that out. Again, that's why looking at a picture is really nice. And so, looking at this, thinking about it, we go over here, and again, I'm looking at this and I'm thinking to myself, well, it looks like as I get closer and closer to -1, right, as I approach from the left and the right, it does look like the function is approaching the same thing, the same y value. So, okay, that's making me feel good. It also seems like it might be defined there. So those two things are making me think, well, okay, well, let's try to plug it in. Why not? Give it a go. It worked the first time. Let's see if it works again. So what does this mean? This means I'm going to erase what I wrote. I'm going to take -1 and plug it in for x. So that gives me 2 -1 squared plus 3 times -1 plus 1 over, okay, bottom, -1 squared minus 2 times -1 minus 3. Okay, so let's simplify. Again, calculator's fine. If you don't have one, that's okay too. 2 plus a negative, 3 is -1, plus 1 is 0. 1 plus 2 minus 3 is 0. Okay, 0 over 0. So, many of you, some of you, none of you, who knows, might look at this and go, the method didn't work, try something else, right? I got 0 over 0, that's nonsense. Hold on. This is called an indeterminate form. Indeterminate form. Okay? What does that mean? It means just this alone is telling you nothing. This could be anything. I mean anything. We are going to see as we go through, and especially when we get to a section later where we do this thing called L'Hopital's rule, we're going to see all of these different examples where 0 over 0 literally actually means infinity, negative infinity, 0, 1, any number you want. It's weird to think about. But all this is telling you, when you get an answer like this, it's just telling you, okay, you tried something, it didn't get you anywhere you wanted. It doesn't mean stop. It means there's still somewhere we can go here. Why don't you rethink the way you're doing this? And so we got to stop here and say, okay, how am I going to rethink this? Well, I've got these two polynomials over each other. When I plug in -1, I get 0 for each polynomial. What does that mean? It means it's a root of that polynomial, right? But we got to remember that. Okay, that means I can factor the polynomial, right? And this x equals -1 should show up in there. So the next thing you should then think is factor. Because if you, the way you got to think about this is, this -1 I plug in is trying to make top and bottom 0, and it does. But if those are both, getting closer to 0 as I get closer to -1. So as I go to -1, there's a root in each of these that is dragging the whole polynomial to 0. But wait, if there's a piece of the top polynomial trying to drag me to 0 and a piece of the bottom polynomial trying to drag me to 0, won't those cancel out? Couldn't those cancel out? And if that's the case, then whatever is left over after I do this factoring is actually what's going to happen with this rational function. I know that's really weird because we've experienced this a lot. A thing inside your function goes to 0, everyone's going to 0. It's taking it with us. But when we have a rational function like this, two pieces both trying to go to 0 at the same time can cancel each other out. Now, I'm not saying that's always going to happen. That's something we can explore. But maybe in this case, this is what's going to happen. So the only way to know is factor. So that means we have to factor the top and bottom, which means we have to rewrite this limit, but we're going to have to factor the top and bottom, okay? So, there's a ton of different ways to do this factoring. You pick whichever way you learned. It totally does not matter to me which way you factor, the box method, the AC method, whatever you do, it doesn't really matter. But, just as an example going through here, so for the bottom, we have x squared minus 2x minus 3, right? So if we're using the AC method, we multiply 1 and negative 3 to get negative 3, and then I'm asking for two numbers that add that multiply to negative 3, but add to negative 2. Remember, that's how that AC method works, something you might want to go look at if you forget how to factor, right? So I'm looking for two numbers that when I multiply them, I'll call them C times D is negative 3, C plus D is negative 2. Okay, because that's how it's going to work when I FOIL, which I'll just kind of mention again when we get there. So, okay, well, what multiplies negative 3? 1 and 3. That's the only thing that's going to work. So one of those is negative, one's positive. So if you try negative 1 and positive 3, I add those, oops, that's positive 2, not going to work. So it's got to be the other way. It's got to be x plus 1, x minus 3. FOIL that back out. X squared, I'll have negative 3x's, a positive x. Those will become negative 2x's, awesome. And then lastly, I'll have the positive 1 times negative 3. That's your negative 3. So, okay, awesome, factored. And so we see here, yep, there is a factor that's trying to get me to 0. But this other factor is not, right? This other factor, when I plug in negative 1, is not 0. So this is trying to go towards 0. So we're going to have to factor the top one, and we're going to have to see if something, similar is going to happen here. So, we can factor the top one. So that'll be 2x. So then we'll have an x here. And when you multiply those, you're going to get 2x squared. That's the only way to break this up to actually get 2 there. Okay, so then we can do a plus 1 here, a plus 1 here. Multiply the 1's, we've got our 1. Multiply the 2x and the 1 and the x, you'll get our 3x. Boom, boom. Now that we've factored, what do we see has happened? Well, exactly what we were thinking. This is trying to go to 0. This one is also going to 0. Okay, we'll put that in green, to 0. So they're both trying to go to 0 at the same time. One on top, one on bottom. But if we're just looking at this in terms of an algebraic expression, and we see this, these terms cancel. An x plus 1 and an x plus 1. One on top, one on bottom, they cancel. So, what does this mean? Well, let's go back up. What did this tell us? If two functions are equal, right, algebraically, we just cancel the term. But if I keep plugging in other x's, I'm still getting the same exact number. So they're equal functions. Then their limits will be equal. So let's rewrite limit x approaches negative 1 of now 2x plus 1 over x minus 3. Algebraically, these are the same function now as I'm away from negative 1. Because that's all the limit cares about. It doesn't care about what happens at negative 1, actually. Just near that, what's happening. Well, remember, near negative 1, as I get close and closer, these two are both really small, trying to go to 0. And they cancel, leaving just this. Now, it's almost like I've restarted this problem. Plug it in. Try the plug-in method again. So let's do it. 2, plug in -1 plus 1, -1 minus 3. That gives me -1 over -4, which equals 1 over 4. Which, it's a little tough to do this, but that looks about right. About 0.25. There we go. So this plug-in method worked, but we needed a little algebra first. Because at the exact point -1, we had both pieces here, the x plus 1, the x plus 1, top and bottom, dragging us to 0, top and bottom. But the key point is it's a limit, so all I need to really be thinking about here is, well, okay, get rid of -1. What's happening right around there? And right around -1, these two terms dragging us to 0 cancel, just leaving the 2x plus 1, the x minus 3. Right, so this specifically is working for us because we actually don't care about -1. We don't care about the moment they're both 0. We care about all the x values right around that. They're not quite 0 yet there. They're tiny, 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 but they're not quite 0. So there we go. Boom. 1/4 is our limit. So let's try another one. I believe this is the second to last one on here. So we've got the limit as h goes to 0 of 2 plus h cubed minus 8 over h. So again, this is actually a pretty similar one, just the algebra will be a little bit different. Give it a go with the plug-in. You're going to get 2 plus 0 cubed minus 8 over 0, which ends up being 8 minus 8 over 0, which is 0 over 0. So indeterminate. We don't know what's going on here. It's indeterminate. So, oh geez, all right, so it's 0 over 0. We don't really know what's going on, but we do want to find this limit. So again, it's now up to algebra. Let's see if we can do some algebra, do some cancellation. Again, it's this idea that there's an h on the bottom. When we're close to 0, this is dragging the bottom to 0. But wait, up here, could there also be something also doing that, trying to drag us to 0 that we can cancel again? And the way that we do this is, well, just do some algebraic simplification. And the algebraic simplification here is, this is a polynomial on top, but it's not in the form that we actually really need it to be. So we're going to algebraically try to first expand this and see what happens. And you're going to get this in this class and other math classes you take, where you don't necessarily know you're going in the right direction. You trust your skills, your algebra skills, you trust the knowledge that you're building in calculus, and you see where it takes you. Sometimes it's going to take you nowhere. I've been there many times. But often it's going to take you to the right place. So we need to expand this out. And you could do this a whole bunch of ways. So this first piece is what we're going to focus on here, right? This you can do, I'll do it the long way first, right? So I'm just going to do 2 copies, and I'll add in the third in a second. There's a formula for this actually, but we'll do it this way first. So this would be 4, so I'm foiling, plus 4h plus h squared. Now that is all multiplied by that third copy of 2 plus h. Okay, so all I did was I just did 2 at a time, and then I'm going to add in the third copy. So this, this is a little tedious, but that's okay. Just hit everything with 2. 8 plus 8h plus 2h squared plus, now hit everything with h, 4h plus 4h squared plus h cubed. Now, that's still all minus 8 minus 8. Simplify. Well, what do we have here? We've got, let's see, an 8 and a minus 8 cancel. And then the rest is just some powers of h's. We have an 8h and a 4h, that's 12h plus 6h squared plus h cubed. Okay, so all together, I know this is a lot, but all together this would be the limit as h goes to 0 of, now what did we just do? We just did the top over h. But guess what? I see an h everywhere. There's an h squared, h cubed, h. So this is actually the limit, and I should put an equals here. H goes to 0 of h times 12 plus 6h plus h squared all over h. And we see what we were thinking was going to happen, right? There's an h on top trying to bring us to 0 and an h on bottom trying to bring us to 0. But as long as we're not actually at 0, these two things are just very small numbers close to 0. They cancel. So all that's left is this limit. So h goes to 0, 12 plus 6h plus h squared, and we try plugging in again. 12 plus 6 times 0 plus 0 squared, and that's our limit. Looks about right to me. There you go. So the plug-in method again works. We had to try it and get something indeterminate. So this indeterminate piece is very important. All it is a little sign that's saying, you know what, good try. Why don't you do a little algebra first? Why don't you try something else? You're on the right track, but why don't you try something a little bit different? But keep going, because there's something to explore here. There's something to learn. We got that the limit was 12. All right, last one. So, you know, based on the pattern, you might say, I bet I know what's going to happen here. Plug it in. Well, we plug in, we're going to get negative 4 squared plus 9 minus 5 over negative 4 plus 4, and as you might guess, 0 over 0. Indeterminate form means get out your algebra skills, let's play around with this. And you know, the problem with this one, maybe you're looking at it and maybe you're a little bit scared. It's okay to be a little scared sometimes with math. I see a square root. Run for the hills. The square root. But whenever you see a square root like this, there's a very common trick you can use, okay? And the common trick you can use is multiplying this by itself almost. Changing this from a minus to a plus. It's called the conjugate. You don't really need that, but that's okay. So the limit is x goes to negative 4. And watch this. X squared plus 9. And I'll talk you through why we do this in a second. Let me just write down what we do, and then we'll talk about like why did someone out there think to do this at some point, right? Okay. So here's the thing. I just multiplied this function by a whole nother thing. I can't just do that because I'm changing it. So I have to do that on the bottom as well. So just be careful. You can change functions algebraically or almost change them as long as you do the same thing in an opposite way to balance that. So the one I'm putting on bottom is just for balance. So at this point, you're probably looking at me like, well, you're not looking at me at all. But if I was there, you'd be looking at me like, come on. I didn't have to simplify this. True, it looks harder. But let's watch what happens. And we're just going to take the top first. So we're just going to look at the top piece just to start. So I've got x squared plus 9 under the radical. And I'm going to multiply that by x squared plus 9 under the radical, but now with the plus 5. So we're going to FOIL, but watch what happens. These x squared plus 9s under the radical, when they hit each other, the radical disappears. Aha! Now it's, you know, not the nicest thing in the world, necessarily going forward, especially the bottom. But that's okay because this actually still keeps getting nicer. Because what's going to happen? I'm going to get this one with a plus 5 and this with a minus 5. That means they cancel to be 0. And all I'll have left is the negative 5 times 5. Look at that. That whole top mess cancels to x squared minus 16. So let's rewrite this limit so you can see it all together. And hopefully, if you're thinking about, the example that we just saw 2 examples ago, you're looking at this one going, that looks interesting. There's something I might be able to do here. So we'll see. But always kind of keep your eye out for what next can I do. So x squared minus 16 over x plus 4 times square root of x squared plus 9 plus 5. Okay. So here's the thing. You did an algebra step. Plug it in. Well, you're going to get 0 over 0 again. But that's okay because we know how to deal with this. Because this piece here will be 0 and this will be 0. But these are both polynomials. Forget about this. It's not 0. Just let it be for a second. These, again, are both polynomials. If I plug a number in and it goes to 0, that's a root. Factor. So let's rewrite this with a little factoring, which is something that I want you to start to see. You get something like this, I want you to be like, immediately, ooh, I bet I can factor that. Is it going to help you? Not always, but it's easy to factor. It could give you information, so you should be thinking about this. So that's going to factor to minus 4 and plus 4, and you'll see what happens. We get a nice little bit of cancellation again. All right, we get the 2 terms, one on top, one on bottom, that are trying to pull us down to 0. But again, if we're not actually at negative 4, it's not going to get us to 0, and so they'll cancel. Very exciting. So we end up with, and I'll put this down here, the limit as x approaches negative 4 of x minus 4 over x squared plus 9 under the square root plus 5. Now we're at the point where we can plug in again. So let's try it. Negative 4 minus 4 over negative 4 squared plus 9 plus 5. Okay, so that's negative 8 over 16 plus 9 is 25. Root 25 is 5. Plus 5 is 10. Okay, that gives me, take a 2 out of this, negative 4/5. Boom. We have got the limit. Whew. This is a two-parter, right? We got rid of this square root. Okay, and let's think about this for a second. How did we do that? Well, if I multiply by almost the same thing, but I flipped this to a 5. Why did I do that? Well, the first reason was when I FOIL this, the square root will go away. Hooray. But then you got to be thinking, whoa. You're going to FOIL this, and the square root will just hit this number, and then another square root will hit this number. I have 2 square roots now. But because we made these 2 opposites, same number, positive, negative, when you actually do that FOILing, they'll cancel. That's the key point, is that we get rid of the square root by multiplying these 2, and then that, we're about to have 2 more square roots, cancel because this is negative 5 and plus 5. That's why we did that. Just a neat little trick. We got to this point, realized, I'm going to do 0 over 0 again, so let's factor. We saw that we can cancel these 2 terms, because again, the limit is not actually plugging in negative 4, it's just near that point. We did the factoring, we did the canceling, we plugged in, and we're good to go. Negative 4/5. So there you go. So, it's gonna get your algebra a little bit, maybe if it's a little rusty. That's okay. You just need to practice. You got to practice your factoring, your FOILing, You might want to just practice your general multiplying and adding. I know that sounds like a crazy thing to tell you in Calc 1, but it just saves you time. We also have a list of laws that you don't need to memorize, but are just good to be focusing on thinking about and playing around with while you're doing limits. So most of these are actually extremely natural, and I think as you're going through, you're going to end up getting to a point where you're using these and you're not even really thinking about it. But it's important to think about them and the limitations. That's the big thing. The limitations of these laws are really what you need to focus on. So let's just read what this says. Suppose that c is a constant, so just some number, and the limits as x approaches a of f of x and x approaches a of g of x exist. This is very, very, very important. We need to use any of these rules. We need both of these limits to exist. This is critically important. Okay? It's very common when you first start out doing these limits. You've got two functions you're adding together as an example here, and you're trying to find the limit of that. Well, this rule's telling you, well, you could just do them separately. That's only something that you should feel confident about doing if separately both these limits exist. So what's a very common case? A very common case where this is not true is if one of these separatlys goes to something like infinity, right? That does not exist. We still write infinity because it's useful to know that the function is just getting bigger and bigger and bigger as we get closer to a, but it still doesn't exist. And so it's common to be fooled by having one of these limits not exist, go to infinity, but still trying to use this idea here. And you'll get stuff like, sometimes you'll get like infinity minus infinity over here, and you're trying to somehow apply that to this sum, and it doesn't work, but you know it's natural. Like infinity minus infinity, I totally understand if you looked at that and you were like, oh yeah, that's just 0. No way. Can't do that. So that's these, when you start dealing with infinities, things get kind of weird. So that's why we just say, don't do that. Only apply these rules if the individual limits exist. This is so, so important. But the great thing is, if you can remember, I can only do these things if each limit exists individually, then all these rules I think are very easy to do. Addition inside, we'll just split it up. Subtraction, split it up. Constant, some number is being multiplied by my function. This is a really useful one. I could just take that number out. If my function wants to head towards 2, the number y value 2, but I'm multiplying that function at every step by 5, well then that 5 being multiplied, that constant, I can move that out. My function goes to 2, the 5 comes back in, multiplies, brings me to 10. So hopefully it's not too bad to convince yourself that the constant makes sense. But then you get, again, multiplication. There's nothing tricky about that. It's just I can split the limit up via multiplication. Division works too, as long as the bottom isn't 0, right? Because we can't divide by 0. So with these rules, hopefully limits now are going to be like, oh, that's really not too bad. I can do a bunch of these examples with these rules. And you can, as long as the limits exist individually. So important. We are often going to run into these scenarios where we're like, oh, this rule is great, but there's a little catch, like this catch here, where the limits have to exist separately. And you gotta that's critical thing you have to be paying attention to. So you don't end up in one of these scenarios where you start getting infinities and you're doing things that just aren't correct. Right? So pay attention to these conditions on a rule, a law, a definition, a theorem that you're using. The conditions here are very important. Work on your WebAssign. Start working on the written homework if you haven't already. And of course, ask me any questions, let me know what help you need, and I'll see you in the next video.